The ultraviolet catastrophe. And in my notes it says here, the ultraviolet catastrophe would change the understanding of physics forever, right? Like, welcome back to physics. So let me tell you a little bit about the background that goes with this. So we have talked about, so this kind of fits in really nicely with what we've done already. We talked about black body radiation, right?
Yep.
You know all about black body radiation. So tell me, what is it?
It's electromagnetic waves. Everything with heat emits.
Uh-huh. Yeah. So anything that has a temperature that's not 0 Kelvin emits EM waves, right? We know this. And we know that the wavelength is determined by Wayne's law, which says that wavelength times temperature is equal to that constant, right? That, what was it, 0.2, I have 898, but yeah. Times 10 to the negative 2 meters Kelvin, okay? So we know that, we understand that life is good. We know what that graph looks like, but we've never really talked about why that graph looks the way it does, okay? The graphs that we looked at when we were in astrophysics, which were the same as the graphs that we looked at when we were doing energy, power, and climate change, they all, if you were going to sketch one, I'm going to let you sketch a graph of that, of intensity versus wavelength. What do those graphs look like? Go ahead and draw that on your paper, just to get our brains again back in the world. And once you've got it, check with your neighbors and see if their picture kind of matches yours. Oh. You're pulling an IB. Jeez. So what does it look like, Lander? A cute little curve, right? Something like this. And then if you had different temperatures, then that peak would be shifted. The cooler the object, it shifts which way? That way?
Yep.
To the right? Okay. So the secret is that we've been doing quantum mechanics all the time.
Wait, the cooler the object is just to the right?
Yeah.
That's accurate. Yeah. It's long ago.
Yeah. Does that make sense?
Yeah.
So this actually is a quantum mechanical effect. If we look at it from a classical viewpoint, if we started out, if we went back and just looked at thermo, and we just started with the thermodynamic stuff that we do understand, and that we understand at a pretty high level, if we look at it, the graph looks like this. Okay. Because the idea is that as the energy goes up, does that make sense? Because as wavelength goes down, energy goes up. As the energy goes up, the intensity should go up. That is a thermodynamics result, okay? So from a classical point of view, from all of the physics that we actually understand where the graphs come from, that's what it should look like, that green curve, okay? And maybe shift it over a little bit. Maybe it's more like over like this, okay? And I think I've got a picture over here. Maybe, is this it? There it is, okay? That blue one is what we think from classical, and this is what we found with experimental data, and that's what we use in astrophysics, and that's what we use now when we're understanding global warming and all of that good stuff, okay? But at the time when this was happening, so this is like 1890s-ish time frame, okay? So this is just kind of to put it in perspective with everything else. This is before relativity had happened. This is before all of that nuclear physics had happened, all of that. We thought it was going to go here. All of the theory said this blue curve should be it. And then those crazy experimental physicists, being all wild and, ridiculous, took measurements and got that red curve. And that caused a problem, right? Everybody was happy. The theorists and the experimentalists were all like, having parties together. Yay, we can agree. And then, dun, 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 those experimental physicists found some weird stuff. It's a problem because it doesn't fit. It doesn't make any sense. And the problem occurs here. What part of the spectrum is that in, friends? It is. It is. And you may have just guessed that based on the name of the story that we're telling. But we could also reasonably understand that that is true, right? Because this would be higher energy. Does that make sense? So the infrared was over here, if we remember thinking about that in terms of, we're talking about like how humans are radiating, they're radiating over here. This is in the ultraviolet. That is where the catastrophe happened.
Wait.
Yeah.
First of all, does the blue classical code continue?
Does it, what'd you say?
Does it continue?
Yes. So the game was that the classical theory was only based on data from like visible and beyond in this direction. Does that make sense? So the theory didn't really have anything to be that was said over here.
Yeah.
But the only thing they understood was that it must continue because it's a nice curve, right?
Okay.
So does that kind of make sense?
Yeah.
I mean, they didn't have any reason to think that it wouldn't until this problem happened.
But so it matches pretty well up to.
Right, up to where we've got this, there's something going on here. This is the problem over here, this nasty drop-off, okay? So this is the problem. This is the ultraviolet catastrophe. And for a long time, they had no idea what to do about this. It was just like, oh, this is too bad. Darn it, I guess we don't understand physics. Okay? There was this guy who I have in my notes said came to the rescue, and it really was quite true. He came to the rescue. His name was Max Planck. Actually, I think I have a picture of him. Do I have, no, where'd he go? There he is, Max Planck.
Oh,
Yeah. Looks like a nice guy. Good German, right? Good German physicist. He looks like a physicist, is that what you said? Yeah, stereotypical physicist, sure. So, here's the thing. Max Planck was a good German physicist, and he was actually quite conservative in his understanding of, he wasn't one of those really outside-the-box thinkers. He knew physics, he knew what he needed to do, and he knew how to put things together. But he also knew that data didn't match the theory, and he was a theoretical physicist. He was a thinker, okay? And in 1900, he developed a theory that did agree with experiment. Okay. And this is kind of like the story that we had when we were talking about the atom and we were talking about the Bohr model. Do you remember we had talked about, we had the alpha particles that were going into the gold foil, and we knew that it wasn't I just told you I was going to call it the raisin bun model, but that's not what we call it. The plum pudding model, right? Okay, it's not that model. We knew something was different, and so Bohr was like, okay, well, this is what must be happening, but I don't really know why. I just know that it kind of has to work this way because it fits really well. That's kind of what Max Planck did, but it was a little bit funny because the ideas that he came up with were really weird. And it was, I have this quote that I can't put my hands on right this moment, but basically he was like one of these, like, we got to follow the rules all the time kind of guys. So the fact that he went outside the box and was like, we have to do something totally weird, not in character, okay? But it's one of those deals where, you guys can think about this in terms of like real life stuff. You know that kid that's always a rule follower, but then feels so strongly about something that they're going to either break a rule or do something that is inappropriate because they really believe in it. And usually people listen to them more. Do you know what I'm saying? As opposed to that kid that always breaks the rule. You know what I mean? It's the same kind of deal. So Max Planck was like, okay, this is how it's got to be, guys. It doesn't make any sense. I don't get it, but this is how it has to be because otherwise what's going on, I don't know. Here's what he said. He said that this black body radiation is produced.
But you didn't say it is a lie.
Is a lie. No, I mean, it does happen. It does happen. It's produced by little subatomic charged oscillators. That's not wild and different. That makes sense to us. That's what I had to convince you of when we were talking about this stuff for the first time, right? You are radiating because you have charged particles in you that are accelerating, and as a charged particle accelerates, it gives off an electromagnetic wave, right? We're okay with that. So that's not the weird, crazy thing. This is the weird, crazy thing. He says that those oscillators can only, I can't write, but let me try that again, vibrate at certain discrete frequencies. Okay? So instead of having a continuous set of options of frequencies that we can have vibrations happen at, they're only this one, and then this one, and then this one, and not in between. It's not possible. That doesn't make any sense. Lander's like, I don't think so, right? And so you're saying, like, what are you talking about, crazy man, right? But he's like, there's no other way to describe it. This is the only way that anybody's come up with yet to describe it, okay? He went on a little bit further. He said that those frequencies are associated to energies, okay? So they're only able to have certain energies. And we can quantify those energies. There's more than one, so I'm going to write this as E sub n, where n is just the index number, okay? Also known as the quantum number. E sub n is equal to n, that value, times some constant we'll call h, times f, which is the frequency. Okay. This constant is now known as Planck's constant. Okay. From my understanding, and I haven't done a lot of reading about this, but from my understanding, it wasn't like he's like, and let's call it Planck's constant after me, right? No, no, no. This was something that was experimentally determined. So my guess is that when Max Planck was actually saying this, he was saying that the energy is proportional to the frequency times this quantum number, this thing we don't know for sure. And then we can go on then to find the constant. Okay. Planck's constant is again marked with H and has a value of 6.62 times 10 to the negative 34th. The units of that I would like you to figure out. I'll tell you that energy here is measured in joules. What are the units? What are the units? What is it? Joules seconds, yes.
Is n just a number?
It's going to be an integer. Yeah, an integer value. Yeah. Yeah. So before, we're going to try a problem with this in just a second here. But before we do this, I want to get our heads into this idea of the word quantum, because I have this list of words. I feel like I need to go out and like do some interviews with people on the street, right? People on the street in Des Moines. What does the word quantum mean? If you ask somebody out on the street, what does quantum mean? What are they going to say? What's that? Really small, right? Yeah, it's really, really small. Is that what quantum really means?
No.
It isn't. It isn't. Quantum comes from the word quantized, right? Yeah. What does that mean? Discrete numbered amounts, right? That's what quantum means. So when we're talking about quantum mechanics, the idea is not that we're talking about little tiny things, but that we're talking about things that have discrete energies, discrete frequencies, discrete values. Does that make sense? That's what we're talking about, not little. So quantum doesn't mean little. It means discrete. Like so this and this and this. Okay? But it's always strongly associated with little. There's a reason for that. We'll talk about that right now. Oops, there's the problem. Okay. So I love this problem. Well, I love it for a lot of reasons. One of the reasons I like it is because it's a really good review of things that we did last year. Springs, yes? Bouncy, bouncy, bouncy springs. This was like a long time ago. This was like maybe about this time last year. Okay? So, you might need those equation packets out. If you do, feel free to pull them out. You have a 2 kilogram mass attached to a spring with a force constant of 25 newtons per meter and a negligible mass. So the spring is an ideal spring. It's stretched 0.4 meters from equilibrium and is released. Find the total energy and frequency of the oscillations according to classical calculations. You can do that. You probably need to look it up, though, because you probably don't have it in the front of your brain, especially after all that pumpkin pie that you ate this weekend. Since Rachel ate like 17 pies by herself, apparently. This is what she's saying, okay? And then, so this one, like this we could have done last year. Then these two pieces are applying the quantum mechanical idea to it, okay? If you need a packet, they're over there on the wooden table, metal tray, bottom shelf. I'm going to give you a little time to get chew on this. You're good? Okay, so tell me what the force equation was, Hooke's law.
Negative kx.
Yeah, F is equal to negative kx, right? So we know that much for sure. Rachel looks excited because she loves calculus. I heart calculus. She has a shirt. Okay, so then if we graph force over distance, and what is force times distance? Yeah, it's work, right? And work is also change in energy. So that's all going to help us there. Is that making sense? Yeah? Okay, so work, and it's always the work energy theorem, right? Gosh, if I can't figure it out, it's always the stupid work energy theorem. Yeah, but it's not F times D, really. It's like F dot D. It's really a dot product. Shh, don't tell. So we need to find the area under the curve. Yes, and we did this last year. I know we did. I remember.
It's a vector.
But if you graph that, then this is the, I'm going to make that an X because D and X are really the same thing. Is that okay? So the force is going to increase as the displacement increases. So that's where that graph comes from. I just took the negative sign out because whatever. I mean, you could do it the other way too. It would work. But so I just like the first quadrant better, I guess. So then you can find the area under this curve because it's just a, what shape is that? It's a triangle. So this distance here is X. This distance here is F. Is that okay? Okay so far? Evan, you look skeptical. You're okay? Whoops, go away. So that means that the work done by the spring on the mass, or the change in energy, in this case it's spring potential energy, is that okay? Is going to be equal to, go away, stupid thing. I don't want you to go away. There we go. Well, that's going to be F times X, but F, well, and it's divided by 2 because it's a triangle. But F is really just KX times x divided by 2. Is that okay? Yeah, I know I did that before. Okay, so that's how you can find the energy. Do you know how to find the frequency?
With that one equation, and you flip them around until the ends work out. Oh. But I don't know where the 1/2, the 2 pi goes. It's over the top of the bottom. I know what you mean. And I don't think I get the order being most perfect. I think I just lost mine.
It's not in there. We could derive that too, if you want.
Wow. Amanda really doesn't want to do that.
But it still would be nice to know where it is.
I don't know that it's in there for sure.
Oh.
Do you want to go through a derivation quickly?
Wait, I have it in here somewhere.
Okay, Lander's going to look it up. Oh.
Come on, Amanda.
It's my first.
What do you want right now?
This is my
I'm just going to go back to our notes from last year. Is that okay?
Sure.
That'll be faster than.
Yeah.
Maybe it'll be faster. We'll see.
I don't know about that.
I love that.
Oh, yeah, I love that too. I did, actually. It's true.
So.
Oh, I saw people working on that the other day,
Yeah.
and I laughed.
Oh.
And was like,
All right, here we
I
go.
don't remember how to do that. Here we go.
Do you agree with this? F is equal to negative kx?
Yeah, we did that.
Yes, is that okay?
Yeah.
Is equal to ma?
Cool.
Yeah? So we can say, oh yeah, and then we had these expressions for x and a that involved cosines. Do you remember where that came from? Do you want me to go back through that? That was from the circle, shoinky, 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 with uniform circular motion.
Yeah.
Keep
And
talking,
then-
or are we okay there?
And then we did calculus.
And then well, not even, we just did algebra, I think, really. Like here, it's just algebra. Because you have a cosine omega t and a cosine omega t, who cares? Like, get rid of the cosines, because that's dumb. So on this side, you're left with, and you get rid of the a's, and you get rid of the negative signs. So you have k is equal to m omega squared. Is that okay? Okay. So then you're left with, tell me if I'm going too fast, or if you need more background. I can do it, I just didn't want to bore you. So omega is equal to k over m square rooted. But omega is also equal to 2 pi f. Is that okay?
Yeah.
That was the piece that we needed to remember for Harry, so that he could remember where the 2 pi goes. And then you can solve it there. Huh? Yeah. Not saying you have to have this all memorized or have this, but it's nice to know where it comes from, right? It's just helpful. So write that down, and then I'm going to move it back to the question again. And it does come from someplace. It's not just crazy talk. Can I go back? Is that okay? There you go. What's what? No, it's angular velocity.
Oh,
Yeah.
velocity.
Yeah. We don't really do angular momentum in here,
Yeah.
unfortunately. I'm going to do it in a couple days in Physics C, though, if you want to stay and play. It'll be fun. Looking forward to it. How's it going? Yeah, that's for a wave. Yeah.
What does it mean by one quantum change?
So we want the change in energy
Yeah.
from E equals, we can say N to E equals n minus 1.
So then, am I just subtracting 1 from that 5.4 times 10 to the 33rd?
Not 1, not like 1, but because you want to know how much energy is there, not what the quantum number will be. So if this is going to be NHF, right? That's how you calculated the first energy, minus n minus 1 HF. Does that make sense?
Okay.
And then if you distribute that in, so it's going to be NHF, let's just keep doing that, minus NHF plus HF. Is that okay if I distribute that 1 in?
Yeah.
These guys are going to cancel. So the change in energy that you'll have from one energy level to another energy level is just going to be equal to Planck's constant times the frequency of the oscillation. And the frequency, as Harry and Rachel were discussing, I just want to make sure everybody heard that, the frequency isn't going to change even if amplitude changes, right? The natural frequency is going to stay the same. So is it a lot of energy in each of those changes? No. Like really not a lot. How much not a lot did you get, Harry?
3.7 times 10 to the negative 4, 34.
Joules? Does that match, Lander? So, is it going to lose a lot of energy between those transitions? No. So much that on our, what we call the classical level, we're not going to notice it, right? We're not going to notice that it's not a continuous curve, that it's these discrete amounts. Because there's so much energy, and each energy transition is so little. Okay? So even though we said that quantum mechanics, the quantum doesn't mean little, it means discrete. This is why a lot of people think that it means little. I mean, average person on the street hasn't done this problem. But this is the kind of context that they're talking about it in terms of, right? There's such small packets of energy that in terms of a mass bouncing on a spring, we don't care. We don't care that it's discrete. We only care if you're looking at something very, very small. Then these discrete amounts really do matter. Does that make sense? That's the dichotomy that we're talking about. Go there and then we'll go here.
As it loses energy, does it change in quantum levels? Quantum levels, I remember.
Yes. So that's what Planck's theory is saying. Yes.
Okay, so like even here from going down from like having all the energy to like 0 energy, that's changing lots of.
Yeah, it's changing like a lot, right? 5.4 times 10 to the 33rd. So if you start this thing off at 40, I mean, that's a big amplitude if we really think about it, right? 40 centimeters. And it's bouncing, and if you leave it going for ages and ages and ages, you come back and then it's like this. It's lost, like it's transitioned quantum levels that many times. That's a lot.
Yeah.
But we just don't see it. It's not like it's bouncing at one level. I mean, it would be, if we could perceive it on our scale, it would be like bouncing, 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 up, bouncing, 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 up, bouncing, bouncing, you know what I'm saying? It doesn't, like, we aren't used to seeing that kind of stuff. Because we don't resolve things that small, okay? We can bring this right back to digital technology, which I know is your favorite thing. And Luis is going to be so sad that he wasn't here today since I'm bringing it all back to digital technology. But do you remember when we talked about like pixel size and we talked about like resolution and that sort of thing? We did all those like little graphs, right? It's the same kind of idea. We're just not looking at it on that small of a scale, so we don't care. So there was this big issue of like, does this stuff really exist? Because before Max Planck, we'd never thought about it like this before. Was it just a brand new kind of physics? Yeah, it is. It's just that we don't care when it comes to all of the stuff that we've been talking about before. So even though I've told you that everything that I've taught you so far in the last 2 years is a lie, it is, but usually we just don't care. We just like sweep that under the rug like it doesn't matter, okay? Because the frog is still going to fall, at about 9.81 meters per second squared, all the way, down and all that stuff is going to happen, even though quantum transitions are happening all the time, right? Right? There's lots of quantum transitions happening all the time. We just don't care. It doesn't matter. Is that okay? So Lander's like, so why did I get up this morning? Well, let me tell you why. Because we do care sometimes. We care when we get to things like the photoelectric effect. Okay, this is pretty awesome. Photoelectric effect. Let me tell you the story of the photoelectric effect. So this phenomenon was first observed in the late 19th century, okay, by a guy whose name you've heard before, Hertz. Okay, he did some famous stuff apparently. Maybe studied oscillations and frequency and things like that. Maybe studied some light. He was the first person to see what was going on here. I'm going to show you a picture of, so this is not of the apparatus, but this is of like a way to think about it. I don't love this one. I just wanted to make you aware of this because this is more similar to what the apparatus really looked like or really would look like if you were doing the lab. I'm going to look at the picture over there because I like the schematic better and it's easier to understand, I think. Is that okay with everybody? So I'm going to go over here. We'll talk through what's happening.
Did you start the recording again?
I think I did. Let's find out.
I just wanted to double check.
Yep, I am. Thank you so much for asking. Now sometimes I forget, so I'm glad you asked. Okay, so let's talk about this thing. Photoelectric effect. Here it goes. So here's the story, and then we'll kind of put some words and things into it as well. But this is what the picture looks like. So you've got two metal plates. Everybody's okay with that? We could also call two metal plates that are electrically connected starts with a C, capacitor. So this is kind of like a capacitor, not exactly, but kind of. And it's in an evacuated tube, so there's no air in there. Okay, so it's in a vacuum. Okay, got two plates. They're connected to a battery. Okay, that's fun. And they're also connected to an ammeter. An ammeter reads amps, so it measures current, right? Okay, so we're measuring the current, and we've got a battery here. And if nothing is happening, so there's no light, and we'll get to the light business in a minute, because you're like, what? How does that have to do with anything? Just wait. But before that, will there be any current? If you've got two plates of a capacitor, they're hooked up to a battery, will there be any current going through here once the capacitor is charged? Like, does that make any sense? Yes, no, talk to me, what do you think? What does a capacitor do? Stores potential, right? So would there be any flow of electrons here? No, so this is gonna read 0. Life is okay. Okay, so you got your battery turned on, and it looks like the way that this is set up, we'll call this the positive, and this the negative, okay? And then we put light into this situation. Now this is weird. We had our electricity stuff and we were happy with that. And we had our light stuff and we were happy with that, but now we're gonna put them together, okay? So light is gonna be shown on this surface, a certain color of light. And the light is going to cause electrons that are hanging out on the surface of this to be liberated. Okay, because if you think about it, what does to ionize something mean? To remove electrons, right? How does one ionize an atom? Put energy in, right? Does this make sense? Put some energy in? Well, light is a form of energy, right? So we're going to shine some light, we're going to put some energy in. Oh, that's going to pop some of the electrons off. That's kind of nice. So there goes some electrons, okay? Depending on how we have this set up, positive and negative, let's put it the other way first, just to make ourselves happier. If I make this side negative, and I make this side positive, so I turn the battery around the other way, what's going to happen to an electron that's freed from this surface? Does it want to hang out near the negative side? No, it wants to go this way, right? So it's going to, dare I say, accelerate in that direction. Is that okay? Coulomb's law, yes. KQQ over R squared, yes. Are we okay here? Talk to me. I need to make sure we're okay. Yes. All right, so we've got electrons are going to accelerate this way. And then, oh my gosh, we're going to have some current. Yes? Is that okay? So that's really what this setup does. Now, depending on how much light is happening here, that will dictate, what's up?
Okay, so
Don't ruin it for me.
Keep going.
Okay, thanks. Depending on how much light is incident here, does it make sense that then some, like fewer electrons or more energy, like something, it might vary the electron stuff? And so that might vary the current? Is that okay? That seems logical to me, at least. I don't know about to you. And let's say that we disconnect that battery for a moment. So now there isn't an electric field. If an electron is kicked out and it's got some velocity, what's it going to do if it doesn't feel a force? What's it going to do, Evan? An electron has a velocity, doesn't feel a force. What's it going to do? It's going to keep moving, right? So does it make sense that if I shine light on here and there's no potential difference here, that some of the electrons will just keep moving over here? Does that seem okay? And depending on the kind of light I'm shining here, those electrons are going to have a certain amount of energy. Could we say it that way? And so even if I put a positive charge here and a negative charge here, does it make sense that some of the electrons might go up here and actually make it across? Does that kind of make sense? Kind of like the frog. I found him. He's right here. Kind of like the frog. If I throw him in this direction, he's actually feeling a force which way? Down. But he's still going to go up because I gave him some velocity in the upwards direction, right? So if we turn our heads this way, then the electrons are going to go up and they might make it across there, might not. We're not sure. It depends on how much energy they have. Is that all okay? Okay. So that's the setup of the photoelectric effect and the apparatus.
Okay, capacitor question.
Yeah.
How come they don't just flow across again?
Because there is not a good, what do I want to say? I just totally lost the word. What's that? Conductor, yeah. Because it's a vacuum, so there's no reason, like, they're not able to move easily.
Okay, so the force.
Right. So if you have a capacitor that allows electrons across, then it's not a capacitor anymore.
Yeah.
Yeah. And a lot of times with capacitors, then they'll put what they call a dielectric in the middle. That's something that is an insulator, so that they're preventing even more so those electrons going across. Does that make sense?
Yeah. But because you don't want it to just stay like that. You want it to eventually, right? Then you store energy, and then though you get rid of the energy, so you let it flow.
No, not across the gap. So, okay, so let's back up for just a second here because I want to make sure this makes sense. So, in a capacitor, let's say you have a capacitor, a light bulb, and a battery. Oops, I probably should have given myself some switches. Oops, that's a really fun switch. It's like really open. I don't want to close! Okay, anyway. So if I close the ridiculous switch, so the light bulb's not involved, right? Because it's not there. That's going to charge the capacitor. Is that okay? And then nothing's going to happen here. Okay? Nothing's going to happen there. And so then I open this again, and so I've got a bunch of charge stored on this, and it's not going anywhere. But I've got a bunch of, what is that going to be? So I've got a bunch of negative hanging out over here, and a bunch of positive over there. They don't really want to be near each other. So when I close this, then the electrons are going to flow through that wire.
Okay.
Does that make sense?
Yeah.
And in doing so, they'll give their energy up to the light bulb.
I thought when Schoenberg taught us, there was a little button capacitor thing where you pressed it and it discharged it or whatever. Like.
Yeah, but
That was that switch.
yes, that's the switch. That it's not the capacitor itself.
Okay.
So like, was he talking about like a keyboard? Because there are a lot, like the old school keyboards, these guys, right? They're actually just all capacitors. And so it's all binary, and if they can, if there's a flow or not a flow. But when you close it, you're not actually like closing the capacitor. You're not, yeah.
Okay, that makes sense.
Yeah. Is that better?
Yes.
Okay.
Much better.
Yeah. I don't feel like I said that exactly right. You're changing the width And so you can allow things, but you don't actually want electrons to flow across the gap. That's not the design. That's the point that I needed to make there in order for it to be a capacitor.
So you're changing the width.
We'll talk about that later.
Okay.
Don't worry about that for now. Yeah, don't worry about that.
Cool.
Okay, is that better?
Yes.
Okay. Are we okay with this setup? Okay. So, as you may expect, because we're talking about quantum mechanics, in the very beginning of the story we said that, like at the very beginning of the day, we said, well, all of this stuff is stuff that doesn't make sense. Quantum mechanics doesn't make sense. Some of the observations that we made using this apparatus didn't lead to things that we expected. So the way that I have this on my notes, and I don't always dictate to you how to write things down, but this one I would encourage you to do. I would encourage you to write 3 columns because it makes the most sense to me to present it that way. So probably better that you make the 3 columns now as opposed to being sad later. So the 3 columns I'm going to label observation. There are going to be 4 observations we're going to talk about. The next column I'm going to label doesn't make sense. Because. And then the 3rd column I'm not going to label yet. Because we'll solve that one later. So let me tell you about the observations that were weird. Like I said, there are 4 of them. First observation. Given that setup, given what we know, first piece of information, no electrons are emitted if the frequency of the incident light is below a certain level. Okay. This level is known as the cutoff frequency. And depends on the material. So I shine light onto this plate. It's a certain kind of metal. And I can measure the electron flow, right? I can measure the electron flow based on the ammeter. And apparently, if I have a frequency of light that is below a certain level, no electrons are coming off. This doesn't make sense because ... wave theory, the understanding of light that we have so far, suggests that energy is absorbed by the electrons, okay? And as that energy is absorbed, eventually the electrons should be emitted once enough energy has been absorbed, okay? It's kind of like when you stand outside, even if it's a cold day, if you stand outside with a black coat on, it's going to absorb that energy from the sun, right, if it's a sunny day, and eventually that black will warm up a little bit. Does that make sense? It's the same idea that we're saying here. That energy should be absorbed by that metal, and eventually those electrons should be kicked off, okay? I'm going to say these should be emitted at any frequency if the intensity is high enough. Number 2, second weird thing. So, and before I tell you the second weird thing, I need to show you one more little piece of the puzzle here. if we set this up so that we have a negative side over here and the positive side over here, does it make sense that we can figure out the maximum amount of energy that this little electron has? When it pops off of this side, what kind of energy does it have? Has kinetic energy, right? And as it moves this way, that kinetic energy is going to turn into electric potential energy, right? Okay. And if it's barely able to make it over there, and I know what the potential difference is here because I can control the battery, so I know what the potential difference is here, then can I figure out how much energy it had there? It's the same idea that if I tell you exactly how high up the frog goes, you can tell me what velocity I released him with. It's the same thing. Same idea. So that makes sense. It makes sense that you should be able to tell what the kinetic energy is of that electron. Here's the thing that we found out. The maximum kinetic energy of an electron is independent of intensity. Okay? Again, according to the wave theory, the reason this doesn't make sense, according to wave theory, electrons are ejected when the oscillations become large enough to tear the electron free. So it's going to oscillate and oscillate, and it's going to oscillate even more and more and more, and eventually it's going to pop off. Okay? That's how we understand it. So according to the wave theory, the higher the intensity, the higher the kinetic energy. Just makes sense. It's just logical. Weird observation number 3. While the maximum kinetic energy is independent of intensity, it does happen to be dependent on frequency. This doesn't make sense because column for this basically says there shouldn't be any connection. It doesn't make any sense for there to be a connection between frequency and energy. You might say, but wait, we just talked about this. Yeah, we kind of did. But according to the theory at the time, this didn't make any sense. Like, this is crazy talk. There should be no connection between energy and frequency.
You go.
Oh, of course. Is that far enough? One more? Ready? Okay. Number 4. If this stuff all makes sense, and by now we're maybe saying maybe not, like this weird stuff's going on, right? But if this idea is true, that electrons are ejected when oscillations become violent enough to pull those electrons off, it would then, like, part of that theory might imply that it's going to take a little while for those electrons to absorb enough energy to tear off, right? To ionize, or to be ionized, I guess. Is that a verb that an electron experiences? I don't know. But anyway, that's what we're talking about here. Okay? That's what we think. But observations showed that electrons are emitted instantaneously right now. It happens right now. Even at low intensity. That is messed up. That is messed up. That's saying that no time is required to absorb energy. So like I said, Hertz made these observations. He wasn't the first one to make them because, you know, or he was the first one, but he wasn't the only one to make them. Because in physics, right, if you just have one person that makes observations, that doesn't help you very much because they may have just screwed up. But we had a bunch of people all over that tried this out, said, oh, okay, this makes sense, like I should be able to do this. And they found all the same stuff. This was happening in the late 1890s-ish. I don't have the actual date, but something around there. It took a while, but this guy finally, 1905, was getting kind of bored, right? Approving patents in the patent office in Bern. 1905 was his big year. We know this, right? Okay. 1905. This explanation is what earned Albert Einstein a Nobel Prize. Go out and ask anybody on the street, why is Albert Einstein famous? What did he get the Nobel Prize for? They would all say, what? Relativity. They'd all say it. I bet they would all say it. That's the wrong answer. He won it for the photoelectric effect. Like, who knows that? Physicists. That's pretty much it. Okay? 1905, this guy shows up. He was just a punk kid at the time. Okay? But he came to the rescue. Again, kind of like Max Planck. He was like, all right, guys, we got to look at this differently. This light business, we've been understanding it so well. We've been understanding it as a wave, right? It's got a wavelength. It's got a frequency. Like life is fine. It's a wave, just like any other wave. But if you look at this experiment as a wave, it doesn't fit, doesn't make sense. He suggested in 1905 that instead of looking at light as a wave, maybe we need to think outside the box and look at light as a what? A particle, yeah. He suggested that light is a tiny, or is a particle, I'll say first. That we can quantize the energy, and we have tiny packets of this light energy known as a what is it? A what? What's it called? What's it called, Rachel?
Photon.
It's a photon. Yeah, yeah. She understands the picture. You guys met my cat before? That's my cat. Her name is Photon. Okay? She got that name because I was doing notes for this at some point, someday. She lived for like 3 years without a name. She was just the kitty. Like, that's what we taught. Like my mom would call, how's the kitty? Like, that was her name. And then I finally decided she needed a real name. And Photon seemed like a pretty darn good name. She's ridiculous. She runs really, really fast. Very, very nearly the speed of light. And she's quite small. She's nearly massless. Okay? So she's a little tiny packet of energy. Okay? She is a photon. Absolutely. So this thing is called a photon. Okay? The idea that he suggested is that we have these little oscillators, right? So we're taking the idea from Planck, because he came up with it first, this little oscillator. And when our spring changes from one energy level to another, that energy has to go somewhere, right? Because energy is always what? Conserved. That energy has to go somewhere, and it goes into a little bit of radiation, a little bit of light. Okay. So these things are emitted when a quantized oscillator, which is every oscillator, okay, changes or lowers, we'll say, energy state. Okay. 1905 was when he wrote his first paper on this. He wrote like 5 papers in 1905, 4 or 5. It was like the revolutionary year of physics. But 1921 is when he really got a handle, or at least wrote about his understanding of light. Okay. He came up with the idea, or he used the idea from Planck, that energy is equal to N times H times F. And so just like you figured out, the change in energy as this oscillator is changing is equal to H times F. And this is the energy of the photon. The nice thing about this, the reason this actually helps in terms of the photoelectric effect problem, okay, is that the photon's energy is localized. Okay? That means that all of its energy can be given instantaneously, by the way, to one electron. Okay. So let's see, I'm going to go back up here and fill in the rest of this chart here to make sure that it makes sense, and then we'll talk about what that means for us. Does that sound okay? So in the other column, I'm going to go ahead and label that with the photon approach. Okay. So let's revisit this real quick. Here we go. Number 1 said that no electrons are emitted if the frequency of the incident light is below a certain level. That didn't make sense in our other theory, but why would that be okay? Why would that make more sense now, given this approach, this idea of light as a photon instead of a wave? What does that mean?
Well, if the frequency is less than the energy the electron needs to go, then
That's exactly right. That's exactly right. So say it one more time with certainty and passion, Evan, because you were there.
if the frequency
Yes.
of the light means photons that are below the energy that the electron needs to cross the potential difference, then it doesn't matter if they give it its energy, they won't cross the difference.
That's exactly right. Yeah. And we can take that even one step further. And if I just give, so if I'm going to try and I'm going to ionize an electron, I need to give it a certain amount of energy, right? Does that make sense? Otherwise, the electron's not even going to come out, let alone go across the gap. If I don't even have enough energy to pop it out, then no electrons are going to flow. So what you said is exactly right. I'm just going to take it one step further and say, if I don't have enough energy even to ionize that material, then no electrons are there to play with. That's exactly right. Let's write it down. So if the energy of the photon is below a certain level, and that's the level where I'm going to say the energy needed to free the electron. That has a special name. It's called the work function. And it's marked with the letter phi. Okay, the 1, 2, 3, 4th from the end, Greek letter. The work function phi. Okay. Then no electrons will be emitted. Okay. So we explained cutoff frequency. Not enough, not a high enough frequency, not enough energy, no electrons. Let's try number 2. So the situation in number 2 said that the maximum kinetic energy is independent of intensity. Does that one make sense? Given our newfound understanding from Albert?
Yeah.
Jack, how does that one make sense?
Because the energy is independent of intensity.
Yes, why?
Well, because it's just equal to the constant times the frequency.
Yeah.
Yeah.
So that, but we have to talk about it one thing at a time, right? Because what energy are we talking about here?
Kinetic energy
Of the what?
of the electron.
Of the electron, and the energy you're talking about is the energy of the
Photon.
photon. So there's one more little step that we need to take. So keep
So
talking.
The electron gets its energy from the photon.
Right.
Yeah.
So one electron gets energy from how many photons? One photon. So 1-to-1 ratio, right? Electron gets energy from photon, and the amount of energy that the photon has is directly related.
It's the frequency that matters and not the intensity.
Correct. Which is exactly what the next one is. Whoa, if you look at number 3, he just said it. Did you hear it? Like he was, whoa, boom. All right, so.
So electrons receive energy from only one.
Yes. Yes.
Why is that?
Because now they're like little billiard balls, right? So the energy comes in, energy goes out. So,
That's right.
so we can talk about it like this. We can say that an increase in intensity of the light is really an increase in what? If we think about light as a photon, more photons, right? Increase in the number of photons. Okay? An increase in the number of electrons results in an increase in the current, okay, which is related to that kinetic energy thing, okay. The intensity does not depend on, or excuse me, the energy of an electron does not depend on the number of photons, but the energy of each. Is that okay? And that actually kind of solves 2 and 3 at the same time. So I'm just going to say 2 and 3. And then statement number 4.
Same kind of deal.
Same kind.
So it doesn't matter how low the intensity is, the intensity affects how many electrons, not it's not some cumulative thing that emits all the energy from this wave. It's the ones that get the photon go, and the others stay there.
That's exactly right. Does that kind of make sense? Okay. All right. So we will start here next time. I hope you guys have a great Monday. There was one other thing that I wanted to say, but I don't remember what it was.